Hi there. The purpose of this video is to choose the correct three-phase motor against particular applications. So why are we talking about three-phase? Compared with single-phase, three-phase, you can deliver constant power. You can deliver the same power with less copper, so you have greater power density. So it sounds counterintuitive. You're going from a two-wire, single-phase AC system, line and neutral, going to a three-wire, three-phase system. And if you go through the math, you can deliver the same power with less copper. Three-phase motors are self-starting, they're simpler design, and they're more efficient than single-phase motors. So what we're going to do is look at three different scenarios and work out what type of three-phase motor that we want to select against a six-person building lift, against power factor correction application, and against a high inertia pump application. So if we look at the six-person lift first, as a bit of background, supply currents into transformers and motors have two component parts to them. They're not physically separate, but they have two component parts. They have a component part that has the magnetizing effect, and they have another part is the work effect, which is the true power, as in the power that gets converted. So if we look at the first application, we're justifying the selection of a motor for a six-person building lift. Squirrel cage induction motor is the simplest, the most cost-effective type of motor for general purpose applications. If we have a six-person building lift, we can work out that really the minimum mechanical power that we need is about 5.5 kilowatts. If we take into account the efficiencies and the weight of the lift, we can come up that really what we need is minimum is a 7 kilowatt power rating for that particular lift. Squirrel cage and motors have got typical efficiencies of about 85–90%, and we would need about 11 amps phase current for this particular type of motor. So squirrel cage is the basic three-phase motor design. It doesn't have synchronous speed. It has effectively constant speed. Once you get up to the point on the torque speed graph where the electrical input is matching the mechanical load, then it does not vary significantly in speed with changing loads. Efficiency is ideally 100%. There are new regulations in place. So what we're really looking for is motors upwards of 90% efficient. So for the particular application of a building lift, you would use a squirrel cage induction motor. It's naturally self-starting. It's very simple design. If you want to control starting current, you can inflow, you can have a star delta starter where you have two coils in there to begin with as you ramp up so that it limits the current. Once up to speed, you switch over to delta connection. The second application is power factor correction. Two ways you can do power factor correction is either by a capacitor bank or by implementing a synchronous three-phase motor that provides leading current to offset the lagging current that will be taken by the factory. This motor is selected only for power factor correction. It's not there to deliver mechanical power or drive a mechanical load. It is not, other than self-starting, it is not an induction motor. Why? Because we've now got a powered DC rotor. Why? Because we want two separate magnetic fields so that we can exactly lock these magnetic fields together. We have a rotating magnetic field from the stator, and then we have a magnetic field from the rotor, north and south from a DC supply. And the idea being is we want the north the north and south to link between the stator and the rotor, so they will link exactly and give you constant speed. Synchronous motor is not self-starting, so generally speaking, it's run as a electromagnetic induction motor initially, and once you're up to speed, you switch over into run mode. Synchronous motors can operate with both leading and lagging power factors. So depending on how you drive the rotor, you can get leading and lagging power factors out of it. For the purpose of what we want a leading current to offset the lagging current of the induction motors in the factory. Our application is for power factor, not for torque. You do get synchronous motors that have permanent magnet rotors. These are typically used for mechanical loading applications, but if you want to adjust the current to offset the lagging currents of the factory motors, then you need to use a powered rotor. Synchronous motors have the highest efficiency of out of the three applications. So typically what you would do is if you, for example, have a 0.85 lagging factory due to all the induction motors inside the factory, you would implement a synchronous motor on the incoming three-phase into the factory to correct it, ideally to have a power factor of 1. So you can go what leading current you want. You can go through the power triangle calculations to work out what leading current you need to supply. So when we add this motor in front of the factory, we do not change the true power. The power that's being converted into work does not change, but what you are changing is the supply current into the factory by adding this synchronous motor. So you can go through the power triangle, and through calculations, you can work out the leading current that you need. And you can also work out the efficiency of this particular motor given particular factors. And typically the efficiency of a synchronous motor would come out to be 95%. It is the highest efficiency of those three applications. For the last application for the high inertia pump, what we want to do is implement a variation on the three-phase induction motor where we've got a wound rotor. So what we're doing here is we're sacrificing efficiency to have high starting torque. How do we do that? We add external resistors in there to control the current flow. And what we do is we sacrifice efficiency through the increased copper loss of I squared R heat loss through these rotor resistors. So we deliberately sacrifice the efficiency for high starting torque through slip rings and adding in external resistors so that we can manipulate the phase shift, and we can have high starting torque. So for application C, for high inertia pump, we need a wound rotor, three-phase induction motor, where we add external resistors in there to control the starting current and hence control the starting torque. Wound rotors are more complicated, they're more complicated design. They've got external resistors in them, as we can see from this diagram. So you're only going to use this particular motor where you need high starting torque, because you have to sacrifice efficiency. The efficiency will be typically 85%, and the cost of that motor will be increased from a squirrel cage because there's more components in there. So you're only going to use it for very particular applications. So we can see here for standard squirrel cage, when we are up on this part here, this slope here of torque against speed is nearly vertical. So it's not synchronous speed, but it does give you effectively constant speed for minimal changes in mechanical load. For the wound rotor, we get significantly higher starting torque. We're talking 4 or 5 times the squirrel cage if you need to overcome the particular high inertia. So the efficiency of a wound rotor is less than the cage due to losses in the external resistors. We sacrifice that. We sacrifice efficiency for high starting torque. So effectively what we're doing is wound rotors increase the R value of the impedance of the motor, the XL part, so you can reduce phase shift and increase torque at low speed when slip is maximum. Thank you for watching.